Good morning everyone, and welcome to today's worked exam answer video. Today I'm taking a look at a structure and bonding question from an AS level paper, an AQA AS paper, and within this structure and bonding question we're thinking about intermolecular forces, but we're also thinking about shapes of molecules, and we're also thinking about examples where certain types of intermolecular force may be present but may not contribute to the highest boiling point, and you'll see what I mean when I go through these different questions, and I'll explain why this particular caveat occurs sometimes, and also let you know how you would spot that that's the case. So we're given some information about 3 organic compounds in the table, and we've got dichloromethane, and we're told that that has a boiling point of 40 degrees and that the molecules of dichloromethane are polar. We're then given tetrachloromethane, and we're told that the boiling point of that is 77, but those molecules are non-polar. And then we've got propan-1-ol, which has a boiling point of 97, and those molecules are polar. Now, before we go any further, what I thought it would be helpful to do would be to draw the structures of each of these 3 compounds, and think about their shapes as I do this. So rather than drawing dichloromethane in a 2-dimensional sort of arrangement like this, where we've got the carbon in the middle, 2 hydrogens and 2 chlorines, I'm instead going to draw it as a 3D tetrahedral molecule. Just figuring out where would be best to do this. I'm probably going to use the space at the bottom here. So the carbon will be at the centre, and then we're going to have 2 hydrogens, and it doesn't matter where I put the 2 hydrogens in the shape, but I've put them both in the plane of the paper, and then using the wedge to show that one of the chlorines is coming out of the page towards us, and the dashes to show that one of them is going back into the plane of the paper. So that would be the shape of our dichloromethane. That would be tetrahedral with bond angles of 109.5. Okay, and we'll come back to these drawings as we answer these questions. Then we've got our tetrachloromethane. So same shape, but rather than there being 2 hydrogens and 2 chlorines, the tetra is the prefix for 4. So all of the positions around my central carbon will be chlorines. So 2 in the plane, 1 coming forwards, 1 going back. That again, tetrahedral. Bond angles 109.5. Then we've got propan-1-ol. So the shape that we're going to be interested in here is around the oxygen in the alcohol's OH group. So what I'll do for propan-1-ol, some of you may not, if you're in year 12, have got onto alcohols yet. So propan, 3 carbons, and then the 1 tells us that the alcohol group is on the end carbon. So that is the structural formula of propan-1-ol. And then it's going to be the oxygen of the OH, which we're interested in the shape of. So if the oxygen's the central atom, we would have our hydrogen and our CH2, CH2, CH3, like that. And the oxygen has 2 lone pairs, like that, and this is based on a tetrahedral shape because there's 4 pairs of electrons in total, 2 bonding pairs, 2 lone pairs, and the 2 lone pairs repel each other the most, then they repel the bonding pairs. So even though it's based on tetrahedral, firstly we don't call it tetrahedral because we only name shapes based on the bonding pairs. So this is going to be V-shaped as opposed to tetrahedral, and we are then going to have a reduced bond angle. It's not going to be 109.5. The presence of the two lone pairs is going to squidge the bonds closer together, so we're going to go down to 104.5 in there. Now, this is important for when we're thinking about intermolecular forces, because whether we have a symmetrical shape or an asymmetrical shape will impact on which intermolecular forces we have present between the molecules. So the tetrahedral shapes can be symmetrical if we've got all of the same type of polar bonds attached as we do in the tetrachloromethane. They may be symmetrical shapes, but because we've got different types of bonds within that symmetrical shape, that then has a different effect to when all the bonds are the same. And then we've got our asymmetrical shapes, like our V shape here, where because the bonds are in one position, sort of in the bottom part of the molecule, and the lone pairs are at the top, we don't have that symmetry in quite the same way as we do with the tetrahedral shape, where all the bonding pairs are equidistant from each other. So we're going to come back to these different shapes as I work through these different questions, okay? So the first question is asking us to state why the carbon-chlorine bonds in both dichloromethane and tetrachloromethane are polar. So when it's asking us about polar bonds, we need to be thinking about electronegativity. When we have non-polar bonds, it's either because we've got the same atom bonded to each other. So in our diatomic elements like H2, O2, N2 and the halogens, we've got a hydrogen bonded to a hydrogen or an oxygen bonded to an oxygen. They're non-polar because there's no difference in electronegativity. It will still be non-polar if there is no significant difference in electronegativity either, and hydrocarbons are examples of this. The carbon and hydrogen atoms, their electronegativity values are very similar, meaning that the bonds between carbon and hydrogen atoms are also non-polar. Every other bond between different atoms will be polar, and with carbon and chlorine, their difference in electronegativity values is fairly significant. Not quite as significant as it would be with carbon to fluorine, but still pretty significant. So what we need to discuss here is the differing electronegativity values of the carbon and chlorine atoms. And that would be the same when you were describing any polar bond. So the carbon and chlorine atoms have different electronegativity values, and we need to remember that electronegativity is a measure of an atom's capability of pulling a shared pair of electrons towards itself when there's a covalent bond. So when we have carbon and chlorine, because the chlorine, my right hand, is more electronegative, the shared pair of electrons between the carbon and chlorine will actually sit closer to chlorine. So then we will assign partial charges where the chlorine will be delta negative and the carbon on the left will be delta positive. So polar bonds are where we have an asymmetrical distribution of a shared pair of electrons. They don't sit in the middle, they sit closer to one atom or the other, and they'll always sit closer to the more electronegative atom. If we have two hydrogens sharing electrons with one another, they will be shared equally. So non-polar bonds are where we have symmetrical sharing of those electrons. So that should be sufficient for 6.1. The carbon and chlorine atoms have different electronegativity values, but I will just add for you guys' benefit. So the shared pair of electrons will be more attracted by the chlorines nucleus. Okie dokie. What we then need to understand is that molecules can contain polar bonds, but the molecule itself might not be polar. So both dichloromethane and tetrachloromethane have carbon to chlorine bonds, as we can see in the diagrams I drew down here at the bottom. But going back to table 4, dichloromethane molecules are polar, whereas tetrachloromethane molecules are non-polar. And the second question is asking us to suggest why the tetrachloromethane molecules are non-polar. And this is where the shapes part comes into this. With our dichloromethane, we have got, well, I'm going to assign some partial charges. The carbon will be delta positive and the chlorines will be delta negative. The carbon to hydrogen bonds will be non-polar, so we can't assign partial charges there. Now what that means for our molecules of our dichloromethane is that we have a region of this tetrahedral shape down in this sort of bottom corner here that is delta negative, has that kind of overall delta negative charge, and then where the carbon is and towards this top section here, this is going to be partially positive. And that means that if we drew another molecule of this, these chlorines would be attracted to the delta positive carbon in the next molecule, and we'd then have the chlorines on another molecule up here being attracted to this delta positive carbon, and those would then be our intermolecular forces, and that would make our molecules polar because those would be permanent dipole-dipole forces. However, if we have all the same type of bond around our tetrahedral shape, we can still assign partial charges where the carbon will still be delta positive, chlorine delta negative, chlorine delta negative, chlorine delta negative, chlorine delta negative. However, because it's the exact same type of polar bond, meaning that we have the same size dipole across that particular bond, so the partial charges are the same size because the electrons are unevenly distributed in exactly the same way in all 4 bonds. Because we have that symmetrical shape, those partial charges will cancel because they're all being exerted in an equidistant way. It's a difficult one to try and think about, it's very abstract, but when we have all the same type of polar bond in a symmetrical shape, the dipoles will cancel. So we're going to need to talk here about the symmetry, which cancels out the effects of the polar bonds, leaving these molecules non-polar. And the reason why they're non-polar is because you won't then have permanent dipole-dipole forces between those molecules. So the tetrachloromethane molecules have symmetrical tetrahedral shapes, meaning the partial charges of the polar carbon-chlorine bonds, I'll just pop my partial charges above there, cancel. That'll do it. Now, when it comes to thinking about boiling points and our intermolecular forces, what you would be expected to know is that hydrogen bonding is the strongest type of intermolecular force. Permanent dipole-dipole forces are the second strongest type of intermolecular force, and van der Waals forces, present between absolutely any molecule at all, those are the weakest. Now, when it comes to thinking about these three molecules, let's have a think about what intermolecular forces that they would have. So I've already talked about the dichloromethane. That would have permanent dipole-dipole forces, which I'm going to shorten to PDD, permanent dipole-dipole forces, and also it's going to have van der Waals because everything has van der Waals. And the reason why this has the permanent dipole-dipole forces is because we have a region that is more electronegative, partially negative here, got a region that's partially positive here, and then if I stacked up a load of these molecules, we'd have attractions between the delta negative on one molecule and the delta positive on another. With the tetrachloromethane, as we've said, all of those partial charges will cancel. Therefore, it won't have permanent dipole-dipole forces because it's a non-polar molecule. So this will only have van der Waals forces. The propan 1-ol, which we aren't asked a question about the propan 1-ol on this page, it was on the next page and it asked you to explain the hydrogen bonding that is present in propan 1-ol. How did we know that propan 1-ol has hydrogen bonding? Well, we have a hydrogen atom attached to, bonded to, one of the three most electronegative elements, which is oxygen. We've also got nitrogen and fluorine. If you have a hydrogen bonded to any of those within your molecule, you will then have hydrogen bonds between the oxygen on one molecule and the bare delta positive hydrogen on a second molecule. So even though we call them hydrogen bonds, they are still intermolecular forces because it'll be this oxygen's lone pair attracting a delta positive hydrogen on another molecule. That would then be our hydrogen bond. This covalent bond here is not our hydrogen bond, that is a polar covalent bond. And so we would have hydrogen bonding, and because everything has van der Waals, this would also have van der Waals. Now, as we just said, the strongest type of intermolecular force is hydrogen bonding. Not surprising, therefore, that propan 1-ol has the highest boiling point of these three molecules. That makes sense. Permanent dipole-dipole forces are then the second strongest type of intermolecular force, and dichloromethane has those and tetrachloromethane doesn't. So we wouldn't really be expecting this. And this is the caveat when it comes to intermolecular forces and boiling points. Dichloromethane has permanent dipole-dipole forces between the molecules, but its boiling point is still lower than the tetrachloromethane, which, as we've established, because of its symmetrical shape, only has van der Waals forces. So this is what this final question is asking us to think about. Explain why tetrachloromethane, that only has van der Waals forces, has a higher boiling point than dichloromethane that has permanent dipole-dipole forces and van der Waals forces. This is a type of question where you would have to be told that the molecules that only have the van der Waals forces between them has a higher boiling point, than the molecules that have permanent dipole-dipole forces between them. If we weren't given those two boiling points and they asked you which had the highest boiling point, well, first of all, they wouldn't do that because they wouldn't expect you to know that even though the tetrachloromethane doesn't have permanent dipole-dipole forces, that its boiling point would be higher. So you'd never get a question like that. If you were given a question where it said, here's three molecules, put them in order of highest to lowest boiling point, they would make sure that the molecules were all of the same MR or a very similar MR. And that, in this case, is not true. We've got dichloromethane, 2 chlorines, 1 carbon, 2 hydrogens. In the tetrachloromethane, we're replacing those 2 hydrogens with chlorines. That's going to massively increase the MR of tetrachloromethane. It's going to increase it by 71. Well, no, the 71 for the 2 chlorines minus the 2 hydrogens that we've swapped them for, so it's going to increase it by 69. Why is that important? Why am I thinking about MR? Because the strength of the van der Waals forces is dependent upon the MR of our molecules, and the bigger the MR, the more electrons those molecules will have, the stronger the van der Waals forces will be. And in this case, what we can clearly see is the increased strength of the van der Waals forces in the tetrachloromethane molecules kind of counterbalances the fact that the dichloromethane has those permanent dipole-dipole forces. So it's the fact that the van der Waals forces are much stronger here because these molecules have a much higher MR than they do here. That only works because the MR is different. And like I say, if we were comparing something like, I'm trying to think of things that have similar MRs or the same MRs here. I don't know why I can't think. If we had like butane and butene, which I know, oh no, that's not going to work because they're both non-polar. Anyway, there are other examples that you will meet where you will get 3 organic compounds and the MR will be similar. Therefore, the van der Waals will be similar. And therefore, you are simply looking for which has hydrogen bonding, if any, which has permanent dipole-dipole forces, if any, and which only has van der Waals, and you would rank them from hydrogen bonding, permanent dipole-dipole, only van der Waals, from highest to lowest boiling point. That's therefore needs to be my answer here. So the van der Waals forces between the tetrachloromethane molecules must be stronger, and it's relative, stronger, not strong, stronger than the van der Waals, and I would definitely write out permanent dipole-dipole in an exam, but I'm going to use shorthand here. Between and that is fact. That is the only way that the tetrachloromethane molecules will have a higher boiling point, if the van der Waals forces between those molecules are stronger than the intermolecular forces we have between the dichloromethane molecules. That's what I've said there. That's what the data tells us. And please always use the data. Some students would get a question like this and say, well, the dichloromethane has permanent dipole-dipole forces, so therefore this would have the higher boiling point. The question clearly says that it doesn't. So if this non-polar molecule has a higher boiling point, the only thing that can make that have a higher boiling point is stronger intermolecular forces. So these van der Waals forces have to be stronger than the combined effect of the van der Waals and permanent dipole-dipole forces here. Then we've got to say why. So this is due to the much larger MR of the tetrachloromethane molecules, and the increased number of electrons which increases the strength of the van der Waals forces. So that's not what we would expect, but clearly the data is telling us that that has to be the case, and it has got quite a bit bigger MR because of those extra 2 chlorine atoms that are present. In terms of the MR and the increased number of electrons, van der Waals forces come about because the electrons within the molecules are always moving, and that can generate temporary dipoles within a molecule, which can then induce temporary dipoles in other molecules. And if you've got more electrons in one place of your molecule at one point in time, that's going to generate a larger partial negative charge and thus a larger delta positive charge across your molecule, which is then going to induce stronger dipoles across other molecules, which is going to lead to stronger van der Waals forces. So that's a very tricky structure and bonding question, because there's a lot of things contributing to the boiling point of those molecules and the polarity of those molecules that we need to understand. So this is definitely a worst case scenario question for an intermolecular forces / shapes question. So if anything that I've said here is unclear, guys, please do not hesitate to get in touch with me, leave me a comment on the video, send me an email, missgtutoring and resources@outlook.com, and I'd be more than happy to help. Hope you all have a brilliant day. Thanks so much for watching.